we move to the second speaker, who is Davide Carbone, which I can see now. Okay, so Davide Carbone, he received his bachelor and master degree in physics in Turin, in the University of Turin, and also the PhD in Turin, but in Politecnico. Okay, during the PhD, he was visiting scholar at the École Normale Supérieure in Paris, in Parisian, and also at the Quran Institute in New York. And nowadays, he is a postdoc at the Torino Politecnico. His work is focused mainly on theoretical machine learning and generative models from the point of view of statistical mechanics, seen in particular as a non-equilibrium system of interacting particles. Indeed, this is also the topic of his seminar today, whose title is Generative Model as Out-of-Equilibrium Particle Systems, Training of Energy-Based Models Using Non-Equilibrium Thermodynamics. Please, Davide, you can start sharing.
So, do you see my slides?
Yes, perfectly well.
Okay, I wanted to minimize this, but sorry. Okay, so thank you everyone for being here. Thank you to the organization for the invitation. Today we talk about a joint work with Mengyan Gua, Simon Kost, and Eric van den Eyden on generative models as out-of-equilibrium particle systems, and I will try to convince you why statistical physics can be important to understand better what's happening in generative modeling. So first of all, since the audience is probably very coming from different fields, I will start from a short history of deep generative models. So what is a generative model? Is a generic map, T theta. So theta is the parameterization of the map, able to bridge two statistical ensembles. So generally, the first ensemble, the one on the left, in this case, is a simple ensemble in the sense that is simple to sample from it. For example, for images, this is just a pure noisy image that is really simple to obtain. And the map is aiming to bridge this kind of statistical ensemble to the target density, rho star, that in this case is, for example, the statistical ensemble describing real images of people. So what we do in practice is that the push forward of samples from rho 0 is approximating rho star. This is the objective. And in literature, we have many different methods. In particular, in the last 15 to 20 years, there were developed a lot of methods, like, for example, energy-based models, normalizing flows, generative adversarial networks, variation autoencoder. And in every case, you have a different definition for this generic map. What I want to stress here is that the overall procedure is the same, in the sense that once you fix the structure of the parametric map T theta, you have to just train the map using the data in some way. This is what you do usually in machine learning. You have some data and you want to train some model. In this case, the model is the parametric map. Probably in literature, you can hear about, for example, cross-entropy minimization, minimax game, depending on the method that you are trying to use, on the generative model that you are trying to use. But in the end, all these names corresponds to do maximum log likelihood. This is something that we like because statistically this is optimal in some sense. You can refer to my PhD thesis, for example, but this fact is very well known in literature, so it's just a textbook topic. So we like maximum log likelihood, and someone of you that is more familiar with generative model may ask about diffusion models, because This kind of generative model is state of the art today for generate images, for example. Well, the idea is always the same. You have to build some map. In this case, I want to stress more what kind of map you are interested in. And the map is just a stochastic differential equation satisfying terminal conditions such that x0 is sampled from the noise and xt is at some t greater than 0 is sampled from the data. So you want to learn, in some sense, these two quantities, the drift and the variance of this stochastic differential equation, such that you can go from the noise to the data. To learn this map that is correspond to then to be able to integrate then the differential equation, you use a simple fact that is the simplicity of the process going from data to noise, because you can always transform the image of a cat in the image of noise, superposing, like you can do it in many ways. The key ingredient is that during this process, you learn some quantity that is able to be is connected in some sense to this mu and sigma for the reverse stochastic process. This is in a nutshell what are diffusion models, and here I put some zoology just because this is really state of the art. You may have read about score-based diffusion. It is the prototype in 2020 was, let's say, put into the game by Song, and then you have flow-based methods. Here I put I highlighted stochastic interpolation, but just because I'm more familiar with that. But flow matching, rectified flow, action matching are other methods that are in some sense related, are more or less the same thing. And then also Schrödinger bridge methods. That is, I mean, it's a bit of a modification. But what I want to convey in this seminar, since I mean most of the audience is composed by statistical physicists, is that nature is a generative model itself, because as I said, statistical generative modeling corresponds to identify a process able to bridge to statistical ensemble. This is what nature does, and this is what most of us probably have studied, because, for example, if you consider this classical problem of a room at temperature T, this is in equilibrium. So if you measure the velocities and the position of the particle, you have an instance, so a sample from a statistical ensemble that you know to be like the Boltzmann-Gibbs ensemble at equilibrium. If you open the window, there's a non-equilibrium process bridging your room to another equilibrium. This is the equilibrium with the environment outside the room. And so the take-home message is that since statistical physics is a very old topic, probably is a good idea to scratch in the literature to try to get some insight on the non-equilibrium process that is bridging statistical ensemble. That maybe can be helpful to train, or maybe to interpret, like to give an interpretation to state-of-the-art generative models. This is an idea that is relatively old now, because in 2015 there was this paper that is very cited, deep unsupervised learning using non-equilibrium thermodynamics, that in some sense is the milestone in this context. In order to convince you that you can learn something and maybe you can improve the way you train generative models using non-equilibrium thermodynamics, I will talk about energy-based models and my line of research. So an energy-based model is a very particular class of generative models because the probability density, that is what we would like to model, the target density, is expressed as a Boltzmann-Gibbs ensemble, where U theta is an energy function, as usual, like this is probably the most cited ensemble in statistical physics. The difference here is U depends on a set of parameters that can be partially or totally weights of neural networks. Like U can be a neural network, or a part of U can be of physical inspiration, and another part can be modeled by a neural network. This is not important. The important fact is that you have this energy, you have the partition function that is defined as usual, and the objective is using the data that you have, so instances of samples from the target density, that can be images, molecules, to train your energy function. For now, you may say, okay, but where is the map? Because you mentioned that generative models are a map bridging statistical ensembles. Okay, for now you don't see it, but in the following slides I will clarify what is it. For now, let's say that it is hidden in the expression of the density. And here, I mean, what I wanted to stress also with this funny meme is that maximizing log likelihood in the case of energy-based models corresponds, this is 2 lines of calculations, correspond to minimize cross entropy. Why I wanted to stress this? Because cross entropy is a quantity that is related to KL divergence. KL divergence is, in some sense, a measure of how much two statistical ensembles are different. And so it's a particularly nice quantity that we like to minimize in some sense. And I want to stress the expression of cross entropy. So you have the logarithm of the partition function plus an expectation computed with respect to the target density of the energy. Okay, let's dig a bit into the problem. What you do, of course, if you want to minimize some sort of energy function of, in this case, of loss function, that is the cross entropy, is to use some usually gradient-based routine. So let's consider the simplest one, that is gradient descent. But of course, for the one of you that are more familiar with machine learning, you may imagine to use also Adam, Adagrad, whatever routine you like that is based on the gradient. So I recall you that theta are the parameters of the energy function u theta, so can be weights of a neural network, and this is the usual dynamics that you have. So you go downside against the gradient with respect to theta. If you compute the gradient of the cross entropy, you have these two quantities. The one in green is good in the sense that you can easily compute it because it's an expectation with respect to the target density. So you can use the samples that you have, the data, so the real images that you have to compute it alongside the training. The problem is that to effectively perform gradient descent, you should be able also to compute the other expectation. That is an expectation with respect to the density that you are training, because U is evolving, and so also rho theta, and you need samples, but you don't have samples from rho theta. And why this is a really big problem? Well, let's fix theta. So for the moment, let's consider just the problem to sample from a Boltzmann-Gibbs ensemble, because maybe someone of you is not familiar with this problem. Well, believe me, there are a lot of studies on that, because as I said, Boltzmann-Gibbs ensemble is one of the milestones in statistical physics. So it's natural to build some routine able to sample from it. But the problem is very difficult. There are MCMC books on score, for example, like you have a lot of methods that you can use. For example, let me clarify why this can be problematic, because if you consider EULA, that is simply corresponding to the Euler-Maruyama discretization of Langevin equation, stochastic differential equation, well, Parisi showed that you can use a method like this to sample from e to the minus u theta. So here you don't have theta because I'm assuming it is fixed. And when the time goes to infinite, you finally reach a sample. You should reach a sample that is that is an instance of the target density. Here there's a typo because this is just raw since I don't have data. But the problem is that for any finite time, the samples x at time k are sampled from some distribution rho k that is not the target e to the minus u. And so if you compute any expectation of any observable using these samples, so using xk, you don't have actually the expectation with respect to rho theta for any finite time. So this is a problem because this bias is something that you cannot really quantify in practice, except for very simple cases, like, for example, the case in which you satisfy some convexity condition. So in very controlled case, you can do the calculations, but in general, you have this bias and you don't know what's going on. And this is a very big problem for energy-based models, because if you use something like EULA or MCMC, you have this bias. And the question is, am I performing gradient descent? Because if the expectation on the right-hand side of the gradient descent routine is not actually what it should be, it could happen that this is not gradient descent. Now, in practice, energy-based models are used, so there must be a solution. And Hinton and collaborators in around 2002, so 2000s in general, thought about possible solutions to this problem, and formulated something called contrastive divergence and then persistent contrastive divergence. The problem is that theoretically it's not so easy to show that they are actually performing some gradient descent. You can do it, for example, for contrastive divergence, but then you discover that actually you are performing the gradient descent on a different, with respect to a different metric that is not the KL divergence, but is the Fisher divergence. But I mean, I don't want to go into details. For now, what I wanted to stress is that actually, if you use an equilibrium sampling method to obtain samples from rho theta and compute the expectation that you need for the gradient descent, you are not performing possibly gradient descent actually, because you have that bias that I showed. So, and here we come to our proposal that is in part related to non-equilibrium sampling, in the sense that let's consider EULA for simplicity. So you have your routine. Now theta is evolving in time. So in principle, what you should do is to evolve this equation for many cases and hope that for fixed theta, you have a sample from rho theta and then do it again and again. So we don't want to do that. We couple this EULA with another discrete map in time for a scalar quantity, AK, that is defined in a very obscure way for now. So you have this alpha case, and this is the definition of this scalar quantity. But believe me, in the sense that if I tell you that you can compute actually the expectation of any observable at any time with respect to the density that is evolving, rho theta, just reweighting with a weighted average. Okay, this is something that you may expect. You have also Jarzynski identity, because in the end you can also compute the partition function at every at every k, where theta is evolving in time. And this is good because you don't have error induced by time discretization. Here there's no error term. And you can also track the partition function. It is something that you like, because in the end, once you train the energy-based model, you have really a probability density. So you can use it to give a probability to each sample that is not something not given a priori for generative models. If I give you an image, it's not given a priori that you can say, okay, this is a good image or a bad image. Nice, but since I'm speaking to statistical physicists, and particularly to physicists, I want to give an interpretation of what is this scalar quantity that we included. Well, if we go in continuous time, you can compute the continuous time limit, and the second equation becomes an ODE of this kind. So you have the partial derivative of u with respect to the parameters, a scalar product with the evolution associated to the variation of theta. Well, let's compute the Ito differential of the energy along a trajectory. This means that you may imagine to be in an environment. So imagine to be in a like on the hills. So you are walking on the hills, and you want to compute the variation of the potential energy, gravitational potential energy that you have while you are walking. So the variation of the potential energy can come, for example, from the fact that the landscape itself is moving. So if the hill on which you are is decreasing in height because of an earthquake or something, you can lose or gain potential energy, and this is the first term. That is what you have here with a minus sign. So what you are using to reweight is the external work, because it's due to the variation of the environment because of an external forcing that is due to theta naught. Then you have the variation due to dissipation, so to the term here that you have in your dynamics, because this dynamics is you are trying to follow the steepest descent, but at the same time someone is giving you random kicks. So you have dissipation in the variation of your energy, because if you go downhill, you are losing your potential energy. And then you have someone that is giving you kicks. So this is something pumping energy in the system in some sense. So it's giving you the energy to stay at some height randomly. And this is the interpretation. And I want to give you a simple plot. So e to the at, that is the factor we are using to reweight, is just e to the minus the work due to the protocol, so due to the variation of the energy due to the external forcing. So imagine to have a Gaussian in blue, and in red you have the associated energy, potential energy U, in the sense of Boltzmann-Gibbs. Then this Gaussian is moving, so the mean of the Gaussian is moving, and now here is 4. I have 2 points, so assume that the points for simplicity are not moving in this setup. So your dynamics is very clear, you are just staying still, but the environment is not staying still because the Gaussian moved. So the red point has an increasing in the energy, meaning that there's a minus, this is suppressed. So if you are interested in computing an expectation against this density, this point is taken less in consideration because its weight is negative, contrarily to the weight of the green point. So conversely, you have a decrease in energy, and so the weight is increasing the importance of that point. Given this interpretation, I want just to show some experiments that we run on using this method. So this is just a Gaussian mixture bimodal. You see that contrastive divergence and persistent contrastive divergence don't get the relative mass in the modes, because once I try to say this at high level. So once the two modes split, if you evolve with a local dynamic like Langevin dynamic or any MCMC that is locally based, what happens is that the workers remain stuck in the modes, and so if you don't separate them correctly, you won't correct that mistake at any time, and so you get wrong inference on the mass that is a parameter of. So the mass in this case is one of the theta, because it's unknown. You want to fit it correspondingly to the data, to the true data. And then you observe that you have monotonically decreasing also for contrastive divergence, but in a different way, as I said, while PCD is not monotonic. And then we try to scale up to other cases, real world data. So MNIST, that is the database of the digits, where we modified a bit the data set. We used just 3 digits and we unbalanced the data set. That is the playground for this kind of method. When, as I said, you have modes separated, and if you don't have a way to non-locally correct the unbalance, you won't infer correctly the number of digits too, for example, in the database, in the dataset. And then cipher 10, but this is just for scaling up the method. And that's it. This is the conclusion. So what I wanted to convince you about is that a generative model is, at the end of the day, some sort of non-equilibrium process bridging to statistical ensembles. So it's something that the statistical physicists could be very interested in, and in particular, we could be interested in applying methods that are for us familiar, like, for example, in this case, Jarzynski identity, but there are plenty of methods in non-equilibrium statistical physics that, in my opinion, can be interesting to be applied. And I tried to convince you using energy-based models, but of course, this is possibly something that one can think about also for other generative models. And with this, I thank you thank you very much for the attention, and I'm here for questions if you have.
Okay, thank you very much. So, is there any question? No. Okay, no questions. So, so we can stop here and close this session. Let me just remind you that the next couple of seminars will be on the second Thursday of March, which happens to be on 13th of March. And that's it. Bye-bye, everyone. And thank you to the speakers.
Thank you very much.